At 121 astronomical units, Voyager hit the sun's invisible border. Yes, that border is real, and it moves. Space has invisible borders carved by gravity, plasma, and light. Picture a boat leaving a harbor, crossing rippling water lines. Space has boundaries like that, only far stranger and fully invisible. Planets, stars, and galaxies all carry their own moving borders. Cross one of these and physics changes its rules. Charged particles bend differently, or gas stops mixing across layers. Gravity's pull wins here, then loses there, creating sharp transitions. Astronomers map these borders by watching matter respond to pressure. Sometimes the line is magnetic, sometimes it is ionization. Sometimes it is simply relativity saying, nothing escapes past here. Today we tour those hidden lines from local to cosmic. By the end, you'll see how edges shape everything. Start near home, where Earth's magnetic bubble meets the solar wind. The magnetopause is the boundary where pressures reach a truce. Magnetic pressure inside balances the wind's dynamic pressure outside. You should care because storms shove that border dangerously inward. Satellites, power lines, and GPS feel the consequences within minutes. Here's how it works in simple physical terms. The solar wind streams past at hundreds of kilometers per second. Its pressure squeezes Earth's dipole, flattening the dayside like clay. Magnetic reconnection opens cracks, letting plasma slip inside the bubble. On the night side, stretched field lines snap, launching auroral storms. Example in real terms with numbers you can picture. On quiet days, the boundary sits near 10 Earth radii. During the 2003 Halloween storms, it plunged inside geostationary orbit. That orbit is about 6.6 Earth radii from the center. Satellites there suddenly sat outside Earth's protection, bathing in particles. Rule of thumb, stronger wind means a smaller magnetosphere, and southward solar fields reconnect faster, punching deeper openings. So this border is alive, and our technology rides it. Pull back to the entire sun, wrapped in a vast bubble. The heliopause is where solar wind yields to interstellar plasma. It matters because cosmic rays flood easier once you cross it, and it marks the outer reach of our star's influence. Here's the working picture, tested by actual crossings. The solar wind races outward supersonically until it slows abruptly. That slowdown creates the termination shock, heating and stirring pickup ions. Beyond lies the Heliopause, a turbulent cushion before the final edge. Pressure balance with local interstellar gas sets the heliopause location. Now the numbers that nailed this down, cleanly and dramatically. Voyager 1 crossed in 2012 at about 121 astronomical units. Magnetic direction changed little, but particles jumped to interstellar levels. Voyager 2 confirmed in 2018 near 119 astronomical units. Energetic particles dropped inside, and interstellar ones spiked outside. IBEX mapped a ribbon of neutral atoms, hinting at global shape. Models suggest a comet-like tail, sculpted by interstellar magnetic fields. Even this border breathes with the solar cycle by tens of astronomical units as wind pressure rises and falls. So the sun's realm ends at a moving, plasma-stitched wall. Now float beside a massive blue star, glowing within a bubble. A Strömgren sphere is the star's ionized zone within surrounding gas. You care because hot stars carve clouds and kickstart new stars. Ultraviolet photons rip electrons off hydrogen, making a glowing plasma. Recombination glues electrons back, stealing photons at a steady rate. Balance those two flows, and you get a sharp boundary. Denser gas shrinks it, brighter stars swell it like lungs. Rule of thumb, triple density shrinks radius by about half. Here's a concrete case with clean round numbers. A star blasting 10 to the power of 49 ionizing photons per second, in gas of 100 per cubic centimeter, carves 3 light-years. That's a neighborhood-sized bubble, visible across a small galaxy. At the edge, temperature and ionization drop almost like a cliff. Gas outside cools, dust survives, and molecules can form easily. Inside, radiation pressure and winds push shells, piling bright rims. The Orion Nebula shows both, within a region about 20 light-years. So young stars draw hard circles, shaping where new stars appear. Shift to a galaxy cluster, thousands of galaxies sharing one halo. The virial radius marks the region that's gravitationally settled. It matters for mass, membership, and where gas stays bound. Mechanically, random motions balance gravity's pull inside that radius. Outside, infalling material hasn't fully mixed or thermalized yet. there is another sharper edge called the Splashback radius. It is where new arrivals swing out to their first apocenter. Dark matter and galaxies pile up there, making a density cliff. One sentence recap: Virial is thermal calm, Splashback is recent arrivals. Numbers help pin this down, and they are striking. For the Milky Way, R200 is about 200 kiloparsecs. That is 600,000 light-years, reaching beyond the Magellanic Clouds. Clusters show splashback features near 1 to 1.5 R200. Observations find galaxy counts drop sharply around that scale. Weak lensing profiles also kink there, confirming the physical edge. Simulations predict colors change as fresh galaxies first pass through, so halos wear outer borders set by recent orbital turning points. Zoom out to the cosmic stage, where expansion shapes limits. The particle horizon is how far light has reached us. The event horizon is what can never send signals here. You care because influence itself ends at these scales. Cosmic expansion stretches space, while light crawls at finite speed. Dark energy accelerates that stretching, locking some regions beyond reach. Mathematically, distances are tracked in comoving coordinates that factor expansion. A handy scale today is the Hubble radius, c/h0. It is about 14 billion light-years, but not a true horizon. Now some anchoring numbers so your intuition stays grounded. Our particle horizon sits near 46 billion light-years comoving. The cosmic event horizon lies around 16 billion light-years away. Galaxies beyond that will never send new light to us. We may still see them now from earlier emitted photons. Think of a boat rowing upstream while the river speeds up. Beyond a bend, no matter your effort, you fall back. So causality has a frontier, set by expansion's changing rate. Bottom line, there is a largest reachable neighborhood in the cosmos. Drop into a galaxy cluster collision, where gas tears and piles. A cold front is a sharp contact between cool and hot gas. It matters because the edge reveals plasma rules at tiny scales. Mergers ram cool cores through hotter atmospheres, sculpting bright arcs. Magnetic draping lines the surface, suppressing heat conduction across it. Viscosity and turbulence decide how crisp that edge can stay. Here comes a concrete case made famous by X-ray maps. The bullet cluster shows a bow shock with Mach about 3. The shock spans hundreds of kiloparsecs with temperature jumps measured. Behind it, a cold front traces the dense core's sharp nose. Chandra images outline edges thinner than a few kiloparsecs. That sharpness implies conduction is highly suppressed by magnetic fields. Another cluster, Perseus, shows nested fronts from gentle sloshing. Waves ripple outward, creating multiple rims across hundreds of kiloparsecs. So collisions draw crisp borders, teaching plasma physics in the sky. Swoop into a young disk, rings of dust circling a star. A snow line is where a gas condenses into ice. Planet formation hinges on that switch, and composition does too. Temperature falls outward as starlight and accretion heat fade. Each molecule has a sublimation point, setting a distinct radius. Icy grains stick better, grow faster, and drift differently through gas. Pressure bumps can trap pebbles, carving the beautiful rings we see. Numbers paint the picture, even for our early solar system. Water ice likely formed near 2 to 3 astronomical units. Carbon monoxide froze nearer 30 astronomical units, forming very volatile ices. ALMA imaged HL Tau with bright rings near 13 and 32. Those radii match predicted snow lines for abundant molecules. Example in real terms, this is comet-making territory. Ices lock gases, then deliver water to rocky worlds inside, so a thermal contour drawn in gas decides planetary blueprints. Now stand dangerously close to a supermassive black hole's shadow. The event horizon is the point of no return. It matters because nothing inside can influence the outside. Spinning holes add an ergosphere where space itself is dragged. Magnetic fields threading that region can power enormous relativistic jets. Here is how the boundary behaves in clear terms. Light can orbit near the photon ring, but not escape. Closer in, all paths end inward, crossing the horizon silently. The horizon radius equals the Schwarzschild radius for non-spinning holes. That radius is 2 gm/c² physically. Numbers anchor this, using the Event Horizon Telescope as reference. M87's black hole weighs about 6.5 billion suns. Its shadow spans roughly 40 microarcseconds on our sky. For Sagittarius A star, the mass is 4 million suns. Gas capture begins near the Bondi radius, far outside. Jets are launched near the ergosphere, close to the horizon. So this border is absolute, yet it organizes everything we see. Those walls Voyager felt are not rare, they are everywhere. Borders separate regions, decide flows, and shape what forms. From Earth's magnetopause to the universe's reachable edge, lines matter. They look invisible, yet instruments and numbers make them plain. We crossed some today and watched physics change at each one. One sentence recap: boundaries appear when forces balance or switch dominance. So the picture is, edges rule structure from planets to clusters. If this tour sparked new questions, share them below. I post deep dives like this weekly. Join for the next one. Thanks for watching and keep an eye on the borders.